We are now in polynomial interpolation. Recall the idea that given n plus 1 data points, you can estimate y given any value of your x. So basically you create a function of x. So here we're going to solve or understand polynomial interpolation using Newton's method. So the idea is simply like this, no? So interpolating polynomial is written in this form. So you can construct a polynomial in this n degree. Okay, so meaning you have x to the n power as the highest variable. So to further understand that one, so example, there are 4 data points, n is equal to 3. Okay, because this one is n plus 1. Okay, so 4 data points, so n plus 1. So we have this expression here, a0, which basically the constant value. Then we have the first degree, a1 times x. Then we have the second degree, and then we have the third degree. So basically this is a third degree polynomial. Okay, so you can express this one as this one. Now with a recurrence system, we can break down p3 of x, or the function of the third degree polynomial can be breakdown into 4 parts. So the first, the 0 degree, so we have the constant, we have the linear, okay, multiplying the constant, the 0 degree here, and we have the quadratic, and then we have finally the polynomial, third degree polynomial. Okay, basically this one is simply combining these 4, we can actually have this expression. Okay, so therefore, having this recurrence formula or recurrence system, this makes us think of a numerical method. Okay, so we have this general formulation for not only n is equal to 3, but for any value of n. So we have first the 0 degree. So basically this is a to the 0. Sorry, this should be 0. Then k, and so follows the same setup or pattern. So we have the constant value here. Then we have the x here. Then the previous function, for example p3, this will be p2. Okay, and k from 1 to n. So basically these are just formulations for this recurrence system. Now there's a reverse engineering. We know that we are not given in a given problem, we're not given with the values, no, of the coefficients. Okay, so we're given with points. So the coefficients of Pn are determined by forcing the polynomial function to pass through each data point, okay, and yield simultaneous equations discussed in the previous module. So basically we are reverse engineering this one. So if you notice, we're given with a0, okay, and then we have y1, and then we have y2, so on and so forth. So with the general formulation, this one, which is quite similar with the general formulation of polynomial. Okay, so then if you notice from this expression, you can actually generate what is what we call the difference equations. So meaning it looks like a slope of a line, or a slope of slope of the line. Okay, I is equal to 1, 2 to the n. Then you have the squared because we have an times a certain value. Okay, so if you so given this one, okay, substituting in this general formula, you can can actually arrive to a solution that a0 is simply y of 0, then a1 is equal to delta y1, okay, for example this one, and then a2 is delta squared y2, which is expressed by this one, okay, and so on and so forth. So basically our goal for polynomial interpolation here is to get the value of your a0, a1, a2, an using the data points. Okay, so that's why somehow we call it reverse engineering. So we have this tableau. Okay, so we will demonstrate. If you still don't understand this thing, we will demonstrate this one step by step in the next lesson. So we have here the function called the coefs, which determine or which look for the value of your a0 and